Okay, another test. So the numerator. So we want to find the limiting this sampling distribution of this ratio, and to compute this, we need to prove this three things. First, the sum square divided by sigma square is so SSB divided by sigma square follows chi-square distribution with a minus 1. So SSB is a variation between groups, right? And we have A groups, so that is a minus 1 degree of freedom. And then this is so this is A times B minus 1. Sorry about that. So second thing is the SS within follows this degree of freedom, and then the two terms are independent. Then it follows the F distribution, right? So that's the goal. So to prove the first one, we note that the group mean follows the mean mu I and variance sigma square divided by B, because we have a B element in each group, and so this is sample mean. So and then these are independent. If I make this transformation, then this is basically normal 0, 1 distribution. If I define Q1, which is the variation between group, then this is just the algebra, and so this one turns out to be chi-square and minus a minus 1 distribution. Why? Because we know that this one is chi-square a, right? And so this one, if you this is algebra, and this one is chi-square 1, and turns out that this one is chi-square a minus 1 if two terms are independent. So Q is chi-square a, Q2 is chi-square 1, and Q1 and Q2 are independent. We can use so what is this? So this is equality by independence, right? And then this is basically MGF, and so the chi-square distribution. What is the MGF? So chi-square A is gamma 2 over A and 2, right? So the MGF is 1 minus beta t minus alpha. So that is 1 minus 2t minus 2 over A, something like that. So basically the point is this guy is 1 minus 2t A over minus A over 2 equal something, right? This one times 1 minus 2t minus 2 over 1. So that means this one should be 1 minus 2t over 2 over A minus 1. So that is the MGF. This is the MGF over chi-square A minus 1 distribution. So that is the proof for step 1. And now step 2, to show the SS within. This SS within. So we can write it as for each group, right? Group I, we have sum of squares, and then we add over A over I. So now to understand this, first note that x1 to xib are IID from normal mu I sigma square. So we can simply use the property of the this is essentially sum of squares. So within each group, so that is chi-square A minus B minus 1, and so each group they are chi-square B minus 1, and then they are independent, so we can take just simply use the additivity of the chi-square distribution. So chi-square plus chi-square is chi-square, and so we just have a degree of freedom, just add up, so that is A times B minus 1. And step 3, to show independence, we for each I we know that these two are independent, and then so the overall these two are independent, and this is the function. So this is SSB is a function of this guy, and SSW is function of this guy, and so these two are independent. That proves the three result, and so that gives the F SSB over sigma square divided by degree of freedom, right? And SS within sigma square divided by degree of freedom, and sigma square cancels, and that. And they are numerator and denominator independent, so they follows F distribution with A minus 1 and A times B minus 1. Okay. We can actually so the previous example is just has one factor, right? So just A groups. So number of group is level. So one factor. But we can actually extend it to 2 factor and 3 factor if you want. So two-way ANOVA is simply the analysis of variance for 2 factors, where factor A has small a levels, factor B has small b levels. For example, suppose that X is a GPA or student in a math department KAIST. Then factor A could be gender. Gender is male or female. And so 2 levels, and factor B could be blood type. Then it has 4 levels, right? A, O, A, B, A, B. So something like that. And so 2A ANOVA, they are interested in testing whether factor A is significant or factor B is significant, something like that. So we're gonna just only consider without interaction case. The extension for other cases is straightforward, but will not covered here. So suppose that we observe Xij for I 1 to A and J to B, where Xij is the response for factor A at level I and factor B at level J. So the total sample size is A times B. Model is Xij is independent with this distribution, but mu ij is the mean of the Xij, but since we have only one observation, so we cannot really estimate all the parameters, so we need a simplify the model. So one example is additive model. Then we can reduce the number of parameters to, so total, if you do this without this one, right, without this constraint, this is a special case, right, additive model. But without this additive model, the number of parameter is A times B plus 1, right? So number of parameter is A times B plus 1, but number of observation is A times B. So number of observation is less than number of parameters, then it's not possible to estimate all the parameters. So we cannot really use this model. We need to do something, and so one approach is to consider this additive model. So the additive model means that there's no interaction term. Interaction term means that so the additive model means that the it's like this. Okay. Suppose we have two levels in A. Okay, 1, 2. 2 levels on in B. So additive model means that the increase is they have equal slope. Interaction term means something like we can have so what, okay, something like interaction term is something like this. Okay, so really So the idea is, so let me explain it a little bit further. So mu 1 2 1 minus mu 2 2, sorry about that, mu 2 2 equals on the additive model, right? So what is this? So for the same I equal 2, right? That is, if you do that, then alpha 1 plus beta 2 beta 1 minus mu plus alpha 2 plus beta 2, right? So under this one. And so that is what? Alpha 2 cancels out, so beta 1 and beta 2. So that means the difference in level j, so mu ij minus mu ij prime has nothing to do with I. It just depends on j, right? So that is the additive mode, j prime. And sometimes we call this mu as a mean effect. So this is a mean effect. This is the difference between, this is the effect for the due to level I in factor A, right? So the mean effect due to level I in factor A. This is the effect due to level J in factor B, something like that. So suppose that we are interested in testing whether the effect for there's no difference. So there's no systematic difference due to the factor B, right? So that is the assumption. Test we wanna perform, and then same story. So we can form the like the function. So this is normal, so everything's easily derived, and under the full parameter space, this is the solution. Okay, MLE, and under the restrict parameter space, we have this is the restriction, right? So we can impose this restriction and solve this. So then using the same argument we can obtain this likelihood ratio, and then it turns out that the numerator and denominator has some. So this is the numerator, right? So numerator and this is the denominator, and then there's some so this is just the algebra. So basically this one making this one less than k is equivalent to making this one greater than c. Okay, and so the next step is we want to find the sampling distribution. So to obtain this one, we basically do similar argument. So this is the numerator quadratic term and denominator quadratic term, and we have a corresponding degree of freedom. So we need to show this one. Okay, so same story. Okay. So the proof is the step one. This part is actually easy because we can just use x bar j. That j is normal, right? Independent normal with what? With the beta. So same. Okay. With the mu, actually mu plus sigma square over a. So we can use this one, j equal to 1 to 1 2 B. So that actually use this one to same story. To prove step 2 and step 3, formally we can use Cochrane's theorem, which is the theorem 9.1.5 in the textbook. The basic idea is that we can this is the quadratic term, and it can be written as v1 plus v2. This one actually is already we showed this one. Okay, this result. So that is the algebra. The interesting part is that Cochrane's theorem says that if this one is chi-square, okay, and also this one is chi-square, then this one v2 is also chi-square. With the degree of freedom, this is chi-square r, and this is chi-square r1. Then this one is chi-square r1 minus r1. Okay, and these two terms are independent. So that means we already show this one is so this part is already known. That is step 1. And so we have only to show that this one v is this one. Okay, so the fact that v follows this chi-square distribution is actually based because we xij minus x bar I, right? For each I follows chi-square b minus 1. Okay, I mean the sigma square. So using this one, basically it's the same thing we proved in here. Similar idea is step 2 here. Okay. So that gives the proof. So you can this is the basic outline of the proof, but details are more complicated. Okay, that's for all for the ANOVA. Thank you.